Hello and welcome to Mr. Jackson's Physics B class, and today we're going to be talking about waves in sound. First thing we want to start off is what's the purpose of a wave? We know what a wave is. A wave is, you can see it on a lake, it's a rise and a fall of the water. And so we have all kinds of waves out there. We've been seeing stadium waves, that kind of stuff. But what it is the water rises and then falls. Okay? But what's the purpose of a wave? Well, if you ever watch a bobber on the water, the bobber actually never moves. It just keeps going up and down, but it stays basically in the same spot. The only reason anything ever moves is because of the wind. Waves do not transfer material. They just transfer energy. So the purpose of a wave is actually just to transfer energy, not matter. So a wave takes energy from one place to another place, and that's what's happening. Okay? And then, how are waves created? Waves are created by something vibrating or oscillating. So water waves are because wind begins to blow on the water and they begin to cause the water to go up and down. So the wind is the beginning vibration for a lake or a water wave. Okay? But there are lots of other waves that travel that we know about. We know of all kinds of waves. Let's talk about those waves and what starts them. So what creates our voice? Okay, what's vibrating that creates our voice? The sound of my voice is making it through this microphone, and what it is I have my vocal cords. And my vocal cords are actually vibrating back and forth, causing sound to be released from my throat. Okay? So there's a vibration that starts it. But as I talk, air moves out of my mouth, but air doesn't move all the way across the room. The energy from my sound moves across the room. Okay? Sound is a form of energy. How about a guitar string? Well, a guitar sound comes from a guitar string. Okay? And that string, when you pluck it, vibrates up and down. Okay? And that's what causes that sound or that wave to be created that crosses the room. But the air from the vibration of that string doesn't move across the room, just the sound, just the energy. Okay? A trumpet. What vibrates in a trumpet? Well, if you're a trumpet player, you'll know it's a person's lips. What they do is they put their lips on a little end piece and they vibrate their lips inside of that, and then the vibration goes down the tube, and the tube, which is the trumpet, amplifies it. Okay? Light is actually a wave, and what makes light actually cause it to vibrate is electrons vibrating up and down inside of an atom, and those electrons vibration give off light. Okay, so these are all things that can give off a wave, and what they're transferring is energy, not matter. Okay, so that's how we understand things. So anything that is a wave, or any wave I should say that started, came from something vibrating. Okay, let's talk about what are two major types of waves. There's two major types of waves. There's electromagnetic waves, which are waves that do not need a medium to move. That means medium means material, and that is light. Light can make it all the way from the sun to the earth without going through any kind of material. Okay, so light does not need material to bounce along. So we got to think about that. So some waves, like people waves at a stadium, needs people. A matter wave is a wave that moves through matter that needs a material to go up and then back down for it to move through. So that would be a matter wave. And a lot of things actually need matter. My voice would not make it to this microphone if there's no air in the room. So we can't yell and send sound through space. Okay? Sound actually needs particles to hit. And so sound comes in, it collides with one particle, which then collides with another, then another, and then another. So sound actually needs a material. That would be a mechanical wave. So a mechanical wave is one that needs a medium. That would be like sound. Sound needs air. So sound will not travel if there's no material for it to stop traveling. So sound can even travel through water. Okay? But sound is a mechanical wave. Mechanical waves need a material to pass through. Electromagnetic waves need no material. Okay? What type of waves can humans detect? And we can detect both. We can detect electromagnetic waves by our eyes. They're sensitive to electromagnetic waves. And our ears are sensitive to mechanical waves. So you need to have air moving in your ears to hear them, but you don't need air for your eyes to see light. That light can travel through space, and your eyes are sensitive to it, whether there's air in the area or not. So you can see through a telescope to a moon or a star, and we can see that light even though there's nothing in space between us and that other planet or that other star. Okay? So we can detect both. We have two kinds of detectors on our bodies for both types of waves. What is a transverse wave? A transverse wave and a longitudinal wave have different parts. We're going to talk about those parts. Let's start with a transverse wave. A transverse wave, if this was our medium, let's say this is water that is not moving, okay, at first. So we'll call this our midpoint. But let's say someone starts to tap it down here, so a wave begins to start, and that wave begins to generate up and down and up and down and up and down. That is a transverse wave. The wave moves to the right, but the material it moves through goes up and down. So they're perpendicular to each other. That's a transverse wave, okay? And one wave peak to one wave peak is called a wavelength. Okay? It has a weird symbol. It's an upside down looking Y, or I think of it as a tent with a tall peak on it. Okay? And that is the distance from peak to peak, or it could be from trough to trough. Okay? Or it can be from midpoint to midpoint, but it has to have a up and a down in it to be a complete wave. So here we have a half of an up and half an up, so we have an up and a down. So this up area is called a crest. This low point area is called a trough. Okay? So we have names for the high points and the low points, and the wavelength is from peak to peak. Okay, so we've gotten 3 of these. And amplitude is how far or how high it goes or how deep it goes from this rest position. Most books will just reference this part right here. We'll just say it's from here to here. That is an amplitude. That's how high or how tall the waves are. Okay, so it's from the rest position to the maximum height. That's called amplitude. Okay. So longitudinal, though, is different than a transverse wave. It's a longitudinal wave. Okay, rather than it going up and down and moving left and right, which means they're perpendicular to each other, a longitudinal wave is considered a wave where the material moves in the same direction. So what happens, let's say we have a slinky. It's just at rest. Here's our slinky. Okay, if I crush the slinky and push on it, what will happen, and I'm going to show it, you have your at-rest slinky, but if you push on it, all of a sudden you make what's called a really tight area, and then that really tight area ends up being followed or leads a really overstretched area, and then another tight area, then an overstretched area, and these little tight areas are called compressions. And that's the wave. That would be the crest. So these are called compressions, and they are exactly like the crest in a transverse wave. Okay? But they're not called a crest because they're a little different. But to make this compression, you have to steal part of the springs to push them over here. Then you have an overstretched area from what it used to be. And so this overstretched area is called a rarefaction. So this area right here is called a rarefaction. Okay? And so this distance right here to right here would be a wavelength. Okay? And so that's how you would measure a wavelength on a longitudinal wave. So this wave, the waves move in this direction and the material is pushed in the same direction. So they are parallel, where here they are perpendicular. Okay? And we'll show some of those in class and also online when we get a chance. What is a pulse? It's basically just a half wave. So if you have a wave and you have only one crest and that's it, that would be considered a wave pulse. Okay? You have to have a pulse or crest and a trough to have a full wave. Okay? But sometimes the book will talk about a pulse. That's not a big thing. Let's move on. What is amplitude and sound and how are they related? Okay, since sound has a wave and sound has an amplitude, how these compressions are pushed together, this amplitude of a sound wave, if I turn it into a transverse wave, the height of the wave is its loudness. So if I wanted to show you a sound that was louder than another sound, then I would just basically show you a really tall wave, and then this would be a loud sound on like a sound meter. If I was going to show you a quiet wave, then this would be a quiet wave. So how high the waves are, okay, not the spacing, not from wavelength. Here the wavelengths are about the same. I'm trying to draw them the same. The wavelengths are the same. It's the amplitude. So when you make a wave higher, then you have, and when it's a sound wave, we have it's louder. It's a louder sound. So on a sound meter, this would be the look versus this for a quieter wave. Okay? So how do we determine the length of a wave? Well, it's pretty simple. You can just measure it. But what if the measurement isn't given for one wave? How could we figure it out? So I'm going to show you a quick little easy trick to figure out the length of these waves. So here we go. Here we see that this wave train, which is numerous waves. Here's a wave train. Here's a very small wave train. And here's an even bigger wave train. How can I tell the length of just one wave? Well, what is one wave? One wave is one peak and one trough. So here's the easiest way. I break these pictures all into crests and trough. So here I see a crest. So I cut it right here. And then here I see a trough. So I cut it here. And then I cut it here. So I've broken it into crests and troughs. Okay? I know that two of them is a wave. But I've got 4 in my picture. So the bottom number is the number of wave peaks and troughs in the picture. 2 of them make a wave because that's the wavelength. Okay? And then I just multiply it by how big the wave train is, and that will tell me how big is one wave. I want just 2 of those 4, so that is equals 1/2 if you simplify it, or 2 times 16 is 32, and then 32 divided by 4 is 8. So in this picture, one wavelength would be equal to 8 meters. And if you want to think of it this way, there's 2 waves, so one wave must be half that number. But this is a simpler method because it works every single time when it gets confusing. So let's count the peaks and the troughs. 1, 2, 3. I see 2 peaks or 2 crests and 1 trough. So I know 2 of these, a peak and a trough, makes one wave. But I got 3 parts, and then I multiply it by 12, and that will tell me how much one wave is. Okay? So 3 times 12 is 24. 24 divided by 3 is 8 meters. So this picture also shows us an 8-meter wave. This one, we can do a really simple method. This is actually only half of a wave. So if I really wanted to see a full wave, I would have to add another half, which would be the same length. So 5 plus 5 is what? 10 meters. So this is a half, okay? And so I need to have 2 full pictures, so there's not enough even there to even see to do this method. So this is just going to be 10 meters. And that's kind of an easy one too. So how big is a wavelength here? Well, let's count our crests and troughs. 1, 2, 3, 4, 5. I've got 5 crests and troughs, but I only need 2 of them, so 2 of the 5 would be a wavelength. And my length is 12.5 from this side to this side. So then I just do my math. Remember, everything on top multiplies. 2 times 12.5 is 25. 25 divided by 5 is 5. So a wavelength in this picture is 5 meters long. So this would be 5 meters. Okay? So that's how you find wavelengths when you know a length of a train of waves. Okay? That would be the simplest method to do that. Amplitudes. What are amplitudes and how are they important in sound? And how do you find amplitudes? Amplitudes are pretty simple. Let's say I wanted to find or determine an amplitude. Let's determine them. I would have to have some more measurements this way. So let's say I have a measurement in right here. From here to here is, let's say it's 4 meters. And my wave goes up to the top and then down to the bottom and up to the top and down to the bottom. Then that means that if that's 4 all the way up, then from here to here is 2. So that would be a 2 meter amplitude. So I would have to have a side measurement to figure out amplitudes. But that's pretty simple as well. Okay? How do we do longitudinal wavelengths? How would we measure those? Well, how you measure longitudinal wavelengths right here is you just measure from crest to crest. So if I have some compression waves, and then you have a rarefaction, then you have a compression, then you have a rarefaction, then you have a compression, you would just need to know what is the distance from here to here. So if that was given, if someone told you that this distance right here, from here to here, is 16, and then you know from there to there, so we got 1, 2, 3 sections, and then I've got 2 compressions right there. So I know from here to here is a wave, so I've got 1, 2, 3 waves. So there are 3 waves in here. So 16 divided by 3 is 5.33. So this would be 5.33 meter per wave. Okay? So all you would do is you would just basically count how many chunks you have and divide it into your length. So if this was 16 meters, you would just divide it by how many longitudinal compression, waves you see complete. Okay? So that's the way of finding wavelengths. All right? Well, let's get closer. We're finishing up here on the types of waves and how we see things. Let's finish up our information here. Okay, let's talk about what is frequency. This is tough for some people, but it's not really all that difficult if we stop and think about it. Frequency is how often something occurs. We're talking about waves. So it's the number of waves that pass a particular point in 1 second. Okay, so let's make a wave train. Here's my wave train. Okay, and how fast it's moving. Let's say right here is a little thing, and this wave is passing through, and every time this peak passes through, this little light right here goes off. Okay, and let's say that the light goes off every 2 seconds. So that would mean, so if it goes off every 2 seconds, we would have 1 wave, and the light goes off of a peak to peak. It takes 2 seconds, and then takes 2 seconds. 1 wave takes 2 seconds. Okay, so its frequency would be 0.5 per second. And when you have seconds on the bottom, so waves per second, it's called, instead of putting that, we call it a hertz. A hertz, H-E-R-T-Z, is how many waves per second. So let's say we have let's say we run this whole thing for 10 seconds. So This light goes on, and these things are being pulled through for 10 seconds. We have 10 seconds, and our light goes off. The light goes off 20 times. So that means from there to there, 20 times. So that means we had 20 waves, and it happened in 10 seconds. So that means it's 2 waves per second, which is 2 hertz. Okay? So a lot of times they don't have the word wave in there, but they just put the word hertz. So hertz just means how frequently something happens. Okay? And we'll get into more about what a hertz is, but I just want to introduce it. But frequency is a pretty simple concept, but it can be confusing because of the word hertz, H-Z. But I just want to explain that to you so that you see that. Let's move on. We're going to do the last couple 3 things here. Let's talk about pitch. Pitch is the frequency of sound. Okay? It's different than loudness. You can play something really loud and it sounds like it hurts your ears, but that could be pitch, not loudness. So let's talk about the 2 different things between pitch and loudness. So here is a sound wave, okay? And here we have a loud one. So we have a lot of high peaks, okay? But then we have a quiet one. And the quiet one has the same wave length, but it's softer. There's a peak there and a peak there. That would be quiet. But how about pitch? Okay, this would be, let's call this one low pitch. And now let's show you one high pitch. But I'm not going to change the loudness. But this one would still hurt your ears a little bit more because it has a higher pitch. So I'm not going to make it any louder. I'm not going to change the amplitude. I'm just going to change how often the wave peak is there. So a higher pitch has a shorter wavelength, okay? Not a higher wave amplitude. Amplitude makes loudness. So this makes loudness, but the wavelength, how close the waves are, makes pitch. So frequency, so if these 2 waves were traveling at the same speed, this one would set up the light more often. It would go beep, 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 beep. This one would be beep, 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 in a sense. Okay? So, and fundamental just means lowest. I gave you that word. Okay? Last couple things is we're going to, how can we change the pitch on a guitar string? You can tighten or shorten the string. If you tighten the string or shorten it, you get a change in wavelength, which changes the pitch. And when you tighten it, you can change the speed. So it's 2 different ways to change the pitch. So here we go really quick here. I want you to draw this wave right here, a higher wavelength and a lower pitch. So here's a wave. I want to draw it at a higher pitch. How do I do that? I just draw these peaks closer together. So I would get, but not taller. In lower pitch, I would just keep it the same height, but I would take it farther apart. So that would be lower pitch. Okay? So those are the basics about waves and their names and their words and what all these words mean. Okay? Thank you for joining me. I appreciate it. You have a great day.